In this video, we're going to introduce Section 11 on carboxylic acids and their derivatives, and this material is covered in Chapter 20. Specifically, we're going to look at 11.1 and 11.2. 11.1 introduces carboxylic acids and their derivatives, and 11.2 will look at the nomenclature of carboxylic acids and their derivatives. Let's begin by introducing carboxylic acids. These are widely found in nature and responsible for some very common odors. For example, acetic acid or ethanoic acid. This is responsible for the smell of vinegar, and vinegar is usually a few percent acetic acid mixed with water. Over here we have lactic acid. Lactic acid is typically the taste or odor associated with soured milk. But what we can see from all these compounds is that this carboxy group is familiar. We have this carbonyl attached to an OH group, and we know that that hydrogen, that proton attached to the oxygen, is very acidic. And so carboxylic acids will have this particular structure. There'll always be that carboxy group associated with them. Now the carboxylic acid derivatives, these are compounds derived from carboxylic acids in the sense that if we were to replace this OH group with another atom or group of atoms, that is referred to as a carboxylic acid derivative. For acid halides, the OH group of the carboxylic acid is replaced by a halogen. In this case, it's a chlorine. So we refer to this as a acid chloride. For acid anhydride, we're going to replace the OH group with this functional group. For the ester, the OH group is replaced with an OR, where R represents some alkyl group. And for the amide, that OH group is replaced with a nitrogen either attached to two hydrogens, as shown here, but those hydrogens could also be replaced by alkyl groups. So you could have a NHR or an NR2. Those are various substituted amides that we could observe. Now, acid halides and acid anhydrides, these are quite reactive. These are highly reactive species, and they're not very common in nature. Whereas esters and amides are more stable, and they're more abundant in nature. Esters, for example, they're often responsible for some fairly pleasant odors. So a lot of the odors associated with fruits are generally from ester compounds. So as shown here, we have methylbutanoate for pineapple, isopentyl acetate for banana, and butyl acetate for pear. You definitely don't have to memorize these, but just to give you a sense that this ester functional group is found quite often in nature. Now, amides are very important to living organisms because they represent the backbone of our protein structures. So proteins are composed of these repeating amide linkages. And if you're taking Biochem 220 or Plan 2 in the future, you'll encounter this quite often. Now let's look at the naming of carboxylic acids and the derivatives. So carboxylic acids, these are compounds that possess that carboxylic acid moiety, or the carboxy group. And when naming, we name the parent and we place the E with oic acid. So methane would be methanoic acid, for example. So again, the parent is going to be the longest chain that includes that functional group, and the carbon atom of the carboxylic acid group will always be carbon 1. The carboxylic acid functionality, as we'll see with the other derivatives, that carbon of the carbonyl will always be carbon 1 in the parent system. So in this example, here we have a 4-carbon carboxylic acid, so this is butane. Drop the E, add oic acid, so it's butanoic acid. And again, we don't have to indicate the locant for the acid because it will always be carbon 1 in your parent system. In this example, we have a substituted carboxylic acid, and you can see how every other group attached to that parent, this is a 5-carbon parent, 1, 2, 3, 4, 5, so that's going to give you pentanoic acid. And we have substituents at 1, 2, 3, 4 at position 4 and 5. At 4, we have 2 methyl groups, so that gives rise to this 4,4-dimethyl. And at position 5, we have the hydroxy group. Now, just to make a quick point here, that we refer to this group as the hydroxyl group, but when we're naming the hydroxyl group as a part of an organic compound, we drop that L. So the overall name of this structure is 5-hydroxy hyphen 4,4 hyphen dimethyl pentanoic acid. Now for cyclic compounds, and we saw examples of this when we looked at aldehydes, if you have this carboxy group attached to the ring system, we will first name the ring system and then add carboxylic acid to it. So this is cyclohexane carboxylic acid. If, like we saw previously, if we were to change the structure of that ring system, let's say we replace that cyclohexane ring with the benzene, this would be benzene, all one word, carboxylic acid. We have seen this shortened to benzoic acid. That is a common name for benzene carboxylic acid, and it's heavily used, but you're always safer, in my opinion, to just name the ring system and then add carboxylic acid to it when naming a structure like this. I also want to point out that if there's substituents attached, let's say there's a substituent attached to that ring system of which you have this carboxy group, this will be carbon 1 of the ring. And so you'll give the lowest possible locant to the substituents attached to that ring system. So in this example, we refer to this as a 2-methyl benzoic acid or a 2-methyl benzene carboxylic acid. Okay, so again, this is going to follow right after, no spaces between any of those letters. Now, the naming of carboxylic acid derivatives is very similar to how we name carboxylic acids. And what I've shown here is a table that I produced that allows you to see how the suffix changes as we go from one carboxylic acid derivative to another. As well, how do we deal with the naming of carboxylic acid derivatives when that functional group is attached to a ring system? And so as we just saw, with carboxylic acids, we replace the suffix E with oic acid. And the ring system, if we have a ring attached to the carboxy group, we name the ring and add carboxylic acid space acid to it. The same strategy is used for the carboxylic acid derivatives, that the acid halide, we drop the E and add OYL, and then name the halide. So if it's a chlorine atom, it's a chloride, bromine atom, bromide, and so forth. And for our acid halide, if we have a ring system, we would name the ring and we would add carbonyl to that name of that ring, space, and then again, list the halide. For acid anhydrides, we're going to identify the acids from which it came. And so if it's a symmetrical acid anhydride, meaning let's say there's 2 carbons on either side, then we would refer to that as an ethanoic anhydride. But as we'll see in a future example, if we had unsymmetrical anhydrides, we would name the 2 acid components. So if it was a 2 carbon and a 3, that would be a ethanoic propanoic anhydride. We're not going to see ring systems associated with acid anhydrides, so that's not applicable. For esters and carboxylate salts, we treat them very similarly in that an ester, we have an oxygen next to the carbonyl, and it's bound to an alkyl group. So we're going to list or name the alkyl group first. That's going to be followed by a space, and then the parent system is named separately, and the ending is replace the E and add O8. Same with ring systems. We're going to identify the alkyl group. The ring system, if it was benzene, it would be a benzene carboxylate, for example. And carboxylate salts, they're similar. The only difference is that instead of an R group attached to the oxygen through a covalent bond, we have an ionic bond or an ionic interaction between a metal cation. So we're going to name that cation first, followed by a space, and then everything else is similar to how we name esters. And finally, amides, we're going to simply drop the E and add amide. So butane becomes butanamide. And if it was a ring system like benzene, it would be benzene carboxamide. As we've already seen, we've looked at aldehydes, ketones, and alcohols, and the endings are all ONE and OL. For aldehydes, as you saw, we end with carbaldehyde. So if it was a benzene, it'd be benzene carbaldehyde if that were the ring system. And we don't have the same type of scenario for ketones and alcohols. The ketone will make up a part of that ring. So for example, a cyclobutane, if it had a ketone functionality within the ring, that would be cyclobutanone. And the alcohol, yes, it is a functional group, but we would simply change the ending cyclobutane to cyclobutanol. So now let's look at some examples of how we would name carboxylic acid derivatives. So let's use the 4-carbon parent, bute. So our first example, we have a 4-carbon carboxylic acid, so that will be butanoic acid. In our second example, we have a acid chloride. And so again, we drop the E in butane and add OYL, so butanoyl. And we identify the halide attached to the carbonyl carbon. It's a chlorine atom, so that'll be the chloride. For this acid anhydride, you can see that I've chosen an asymmetrical acid anhydride, where on the left-hand side we have a 4-carbon parent, whereas on the right side we have a 2-carbon parent. So bute would represent this parent, eth this parent, and we would alphabetically order those particular parents. So this would be a butanoic space ethanoic anhydride. For the ester, we're going to have the ending O8, and similar for the carboxylate. So again, we have a 4-carbon unit, but for esters, we're going to start by naming the alkyl group that's directly bound to the oxygen. So we have an ethyl group. So this would be an ethyl space butanoate. And similarly, we have for the carboxylate, we're going to just identify the metal cation first. So we have a sodium cation. So we simply would refer to this as a sodium butanoate. And for the amide, we have butanamide. So we drop the E, we add amide. And the following amide, what I've done is shown a different scenario where we have alkyl groups attached to the nitrogen of the amide, as well as an alkyl group attached to the parent. And for naming of amides, we would identify the substituents attached to the nitrogen using the locant uppercase N. So we don't use a numerical locant to represent any alkyl groups attached to this nitrogen. Numerical locants are only used to identify substituents off the parent, and the parent starts at carbon 1 of the carbonyl and goes to the left in this particular structure. So for this example, we have a methyl group here and here and here. So this will be a trimethyl substituted butanamide. But we're going to indicate that using a mix of the letter N. So it's N, comma N. And this is a 1, 2, 3 trimethyl butanamide. And so it doesn't really matter how you order these particular locants. Typically, the letters will precede the number. And so that might be my preference or suggestion to you when carrying out Wiley Plus type questions. Now let's look at some examples where we have ring systems involved, and we have the functional groups of the carboxylic acid derivatives and carboxylic acids directly attached to those ring systems. So for this one, as we saw previously, we would name the ring cyclopropane, carboxylic space acid. So it's all one word, cyclopropane carboxylic acid. And for the acid halide, here we have a bromine atom, so this will be a bromide. We would refer to this as a cyclopropane with a 3-membered ring. All one word, carbonyl space bromide. All right, and for the ester, this is going to be, first we'll identify the alkyl group attached to the oxygen. So we have a methyl group. We'll have a space, and then cyclopropane carboxylate. And finally, for the amide, we have, in this case, cyclopropane carboxamide. So if you have any questions about the naming of carboxylic acids or carboxylic acid derivatives, by all means, send me an email. Thank you.